Hello everyone and welcome to another episode of Nowhere Yudarris. Today we'll be talking about general chemistry's own bonding and chemical interactions. This is your host, Mahmoud Nowhere. Don't forget to like, share, subscribe, leave any comments, and check out our TikTok as well, alright? So let's dive deep into bonding. So we're gonna start with formal charges. What is a formal charge? Formal charge tells us if the atom is sharing its valence electron in the best way, and its formula is Fc, like formal charge, is equal to valence electron minus N is the non-bonding valence electron. So you see here in the oxygen, for instance, you got like 4 valence electrons that are not bonded to anything. And then you got B divided 2. That's the total number of electrons shared. So let's say, for instance, C, the carbon. Okay, how many valence electrons does it share? It shares 8. It shares with oxygen and it shares with the other oxygen, etc. So having a formal charge of 0 is the best structure. But if you don't have a 0 um, as a formal charge for your structure, the next best structure is the one with the least formal charge. And then you got resonance structure. Resonance structure is basically when there is double or triple bonds, and then the central atom needs to, rotate and share with the rest of the atoms it's bonded to. Next, you have dissociation energy. BDE. BDE is energy required to break a bond, and it can be homolytic or heterolytic bond cleavage. So homolytic is one electron of the broken bond goes to each molecule. Alright, so they both, let's say, I don't know, they both shared an electron each. They both get their electrons back. But with heterolytic, let's say you have NaCl bond, now bond is broken. This is positive, this is negative. Na just gives up its electron, Cl takes the electron, and it becomes an anion and a cation. Alright, that's that. And whoopee, what's happening here? So what a Lewis acid is say electron pair acceptors such as H plus, hydrogen plus, Fa2 plus, zinc, chloride and FABr3. Lewis bases an electron pair donor such as Cl minus and H3 as CH3. Now we come to the important part. What is Vesper theory? Vesper theory states that electrons move away as far as possible. They repel each other, they don't want to be near each other, so they try and move away as far as possible, and that creates structures for us. First, we have linear with a bond angle of 180 degrees, right? And it's usually an sp hybridization. I'll tell you guys what that is later. And an example of that is BeCl2, so imagine Be in the middle, Cl on the side. Trigonal planar with a bond angle of 120 degrees here, central atom, 3 bonds, and it's the sp2 hybridization usually. An example of that is BH3, tetrahedral bond angle of 109.5. See, this is the example here, sp3 hybridization. And an example of that CH4, methane, trigonal pyramidal is next with one lone pair and a bond angle of 107 degrees, and it's a sp3 hybridization as well. An example of that is NH3. And next we have bent, which is two lone pairs and a bond angle of 104.5, and it's an sp3 hybridization. Example of that is water. Okay, so the shorter the s character, the stronger the bond, and it's closer to the nucleus. The more p character, the weaker. Alright, so we said for instance linear is an sp. Alright, what does sp mean? An sp means it has one sigma bond and two pi bonds, and it's the strongest. Alright, a triple bond is the strongest. So an sp is basically a triple bond, and it's the strongest, and when it has a one pi bond and one sigma bond and two pi bonds is the strongest because it's the shortest. That's when a triple bond happens. Next, you have a double bond. So a double bond has one sigma, one pi, and it's the second strongest, and we call that sp2, like we mentioned here with the trigonal planar bond. And then lastly is sp3, which is a single bond, and it's a sigma bond, and it's the weakest because it's the longest. All right, let me explain this concept real quickly. All right, so let's say you got linear. You got, for instance, C. All right, let's say sp. And it's the strongest because it's the shortest. It has less p character, it has s character. Alright, so having an s character and having it be two pi bonds and one sigma bond, and it being a triple bond, it means that it's really close to each other. You see how like the attraction forces between both carbons are? So this triple bond is really strong, and this is how you label it. So a triple bond sp, it's the strongest out of the other bonds. Next you have, for instance, we said for the trigonal planar, BH3, BH3, alright. In this case, alright, a BH3 is because, are there any double bonds? Nope, there aren't, so it's a single bond. But let's say there was, let's say for example, there was here a, that's bad drawing. Let's say here there was a double bond though. Alright, we just for the sake of explanation, we'll say there's a double bond here, so an sp2. So an sp2 has one sigma bond and one pi bond, right, making it the second strongest out of them. Alright. Next, we're gonna have methane. So we're gonna have like CH3, 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 so CH4. Why am I saying CH3 for? Alright, so you see how the carbon can't bond anymore? Its valence electrons are done. Boom. You know, oh, it's connected or it bonded to each of the hydrogens already. Okay, so it's an sp3. And I can't even draw properly or write properly today. So it's an sp3. What's an sp3? sp3 is the weakest. It has the most p character in comparison to a s character, so it's 3 to 1. P character is to a and s character, and it's the longest. Okay, and it's a single bond, and it's the weakest. All right, because it has one sigma bond. All right, so an sp is attached to two groups or one atom and one lone pair. As you can see here, it can also have one lone pair. By the way, lone pairs count as a group as well. It doesn't have to be just an atom. An sp2 is attached to three groups, or for instance, two atoms and one lone pair, or in special cases, two lone pairs and one atom. Next you have sp3, which is attached to four groups, including atoms and lone pairs. Like we see here, for instance, in trigonal pyramidal, it has one lone pair, three atoms, and in bent it has two lone pairs, two atoms, so mix and match. Alright, so in addition to knowing if they're polar or non-polar, we also have to know if they're symmetrical or non-symmetrical, because with symmetry it helps to know if the dipoles cancel out. So symmetrical molecular geometries are linear and trigonal, planar, tetrahedral, octahedral. Alright, just for now memorize these: linear, trigonal, planar, tetrahedral, octahedral. Alright, so even if they have polar bonds in an atom and they cancel out, they result in a non-polar. Alright, so there's that. Next, we have the intermolecular forces. Alright, intermolecular forces are forces of attraction or repulsion between molecules, and the main types are London dispersion forces, dipole-dipole forces, hydrogen bonding, covalent bonding, and ionic bonding. So London dispersion forces are the weakest of the intermolecular forces, and it happens between nonpolar molecules or between molecules that doesn't have any permanent partial charges. Then you have the dipole-dipole forces, which basically happen between polar molecules, and it's stronger than London dispersion forces. And these forces, as a matter of fact, arise due to the attraction between partial positive charge and the partial negative charge of another molecule. That's a dipole-dipole. uh, you want to remember it by, it's between a dipole, like a positive dipole, and a negative dipole. Next, we have a hydrogen bonding, and a hydrogen bonding happens between a hydrogen atom and highly electronegative atoms like oxygen, nitrogen, and fluorine. All right, oxygen, nitrogen, and fluorine. These are the most common, the strongest, because they're electronegative AF. All right. And then you have covalent bonding occurs within a molecule, and this includes the sharing of the electrons between the atom, and this type of bonding is really strong and requires a lot of energy to break. Lastly, we have the ionic bonding, and it's the strongest out of them all, and it happens between a positively charged ion and a negatively charged one. This type of bonding is found in like ionic compounds such as salts, and they have a crystalline structure. And that's that. Please let me know if you have any questions. I hope you enjoyed today's class, and have a good day. Don't forget to subscribe and to share the video if you liked it and like it.